Welcome to the lecture 30. This is about multi-dimensional distributed hash tables, which we are going to talk about in this lecture. So as we understand, node IDs are a long string of bits which are used in any DHT system. So roughly it's going to be 256 bits or even higher. And in chord and pastry, they are being mapped to a circle. And then on that circle, depending on where the hash ID lies, we define a distance metric and then correspondingly who will be the root node for every hash ID. So in chord, for example, it will be a unidirectional movement which is permitted. So in the direction in which the node IDs are increasing, in that whichever node is closest to the hash ID, that will become the root node. In case of pastry, on that circle, whichever is closest in terms of numeric distance, or basically difference between the two node ID and hash ID, that will become the root node. Cadmilia and tapestry works in slightly different fashion. So they, for example, in Cadmilia, we are actually take the first bit of the hash ID, we compare with a node. So a node actually is going to, we are going to choose either 0 or 1. So if you are at this particular, if you are at any node, you will find out if the first bit is matching with this, it's perfect. So you go on this side and then there is going to be another circle where the current node which I am talking about is here. So current node was here, current node is here. If it matches, it goes into another smaller circle and so on. Otherwise, it goes on to the other side. So I am showing circle because the same thing gets extended to tapestry, where instead of 2 points where we are just bifurcating, we start actually using a circular arrangement of the digit values, which are not, for a bit these are only 2, for a digit it will be more. So for a tapestry, for example, with hexadecimal digit, there will be 16 such entries. One will be occupied by the current node and there will be one nodes corresponding to each other entries if they exist. Okay, so it will be depending on which bit I am talking about. So here we will be handling bn minus 1, here we will be handling bn minus 2, here we will be handling bn minus 3 and so on. So on a similar lines, when we go through this multi-dimensional DHT, we will probably appreciate better tapestry and Cadmilia. So node IDs are supposed to be fragmented or partitioned into multiple partitions. In Cadmilia, they are being partitioned, every bit is created as a separate partition. Here they can be F1, F2, F3 and F4. But for simplicity's sake, to understand everything, let's take with only node IDs with 2 fragments. So I call it NX and NY. Now once you have NX and NY, they are like X-axis and Y-axis argument. So they basically, now node ID can be represented as a point in 2D space. So a figure will look something like this, where X dimension is in this direction and Y dimension is in this direction. So here HX and HY are the hash and these three are the node IDs. So HX will, whichever node is going to be closer. Now closer essentially can be Euclidean distance. So where I can actually compute the distance as Hx minus Nx square plus Hy minus Ny square root. So I can minimize this distance and find out node such that this happens, and that will become the root node. Second possibility is I can actually take precedence of one axis over other. So first of all, find out somebody who is going to be closest to Hx. Okay, for example, in this case, if I am looking at in X direction, so closest can be this. If I am not using a cyclic distance, the way it happens in chord, if it is, there is a fold over of the dimension, and if I am looking in only in one direction, this guy probably closest because this is closer than this node. So you will first of all hand over to this, and this guy will now look in this dimension who is the closest in with Hy. And now one thing which we need to understand, that these nodes points are, or the nodes are not placed arbitrarily, they have to be on a mesh, because they don't, only values of the axis which are allowed are integer values. We don't allow non-integer values to be there in the node IDs. So let's look at a case with the wrap around. So here the wrap around actually has been done. and I have placed these red colored dots are the actually nodes which are placed. There is hash ID also which I have shown. Now because of this wraparound, this will look something like a torus. This is a two-dimensional torus, the way it has been flattened up and shown that way. And if it is there, not only nx, ny, nz is there, it becomes a three-dimensional torus. If you have n partitions, it will become an n-dimensional torus. Okay. Now all node IDs will be at the points on this grid. So as I am saying that first, instead of going with Euclidean distance, we can look for non-Euclidean stuff. So let the precedence be given to node x-axis, and it is a wraparound, so it will go only in one dimension in a circular arrangement like a chord. So let's all find out who is going to be the hash ID for for 33. So we assume that the query is starting at 86. So 86 is supposed to maintain a routing table. So how it's going to maintain? So maybe first thing which you can do is that it will maintain because nx is 8 for this node. So with nx 9, any one of the node entry has to be present. So I call it 9x. So x means there can be anything which can be put here. There can be anything which can be placed there. And then, but there is no node in that column, so we actually going to leave it. 0x, similarly there is nothing. 1, 2, 3, we'll put the entries. Some places you can have two possibilities. For example, this one, I could have put 2, 0 or I could have put 2, 4. So 2, 0 has been put. In fact, there is a possibility here that we can use proximity metric, which we have talked about in pastry routing. So basically, who is closer to you in terms of either number of hops or in terms of round trip time delay, and then based on that, the one which is closer to you can be chosen and put. So that will optimize the performance of your DHT system. Now another thing which you should note here is that on x-axis I have only 0 to 9, while on y-axis it is 0 to 6. While in Tapestry, all digits were of the same memory system. So either you are using hexadecimal or octal. But in this kind of arbitrary partitioning, I can use any modulo system for any digit. Okay. So I am using modulo 10 and modulo 7 here. So the way the rule is now, from 86 it will search for a node with the smallest nx such that it is greater than or equal to 3, because I am searching for 3, and it has to be done in a cyclic fashion, the way it is done in the chord. So there are two options. 86 could have chosen now for so anything which is greater than 3. Essentially we have to figure out either now equal to condition is going to match, so either 3.2 or 3.5, but both of them will not be there with 8.6. So if 8.6 has 3.2, so query should be handed over to 3.2 in that case. So 3.2 is in second column, keeps all the nodes varying with ny. So there will be two columns in the routing table. It's something like Tapestry. The first column, I am actually first bits, all possibilities are taken with x. Second column, we keep whatever was our value 3, and then of course we will try all 0, 1, 2, 3 and x in that fashion. Okay. So since there is no x, there is no third dimension, this x will not be present here. So this will not be there, this will not be there. So all nodes, so whichever are present, otherwise there will be a dash entry, no entry in the routing table. So 3.2 in second column will keep 3.5 as well as 3.2. And then it will try to find out who is again in cyclic fashion, which is the ny which is smallest but greater than or equal to 3, which in turn out to be 3.5. 3.5 also can do the similar search and will find that it itself is the closest node. So therefore it will declare itself to the root node and search for the key value pair which has come in the message. So similarly we can do the search for hash ID of 4.1. So hash ID of 4.1 when you do, so query, and we assume let the query start from 2.0. The query starts from 2.0. So once the query starts from 2.0, this need to be handed over to 6, because that's the only thing which is available greater than 4. So it can be 6, 2, 6, 3, 6, 4. So if 6, 3 is the entry in the routing table of 2.0, it will be handed over to that. And 6, 3 will have all nodes in that column, 6, 2, 6, 4 in the second column actually of 6, 3's routing table. and as 1 lies between 4 and 2, query should be handed over to 6.2. So 6.2 will then search, it will find that it itself is a root node, so the query will stop there, and then query can be searched in the query database. Okay, so this is how typically, this is very similar to what happens in Cadmilia. This happens in Tapestry. The same thing happens in Cadmilia. Of course, each dimension will have only 2 positions in that case. So Cadmilia becomes an n-dimensional torus with n bits sitting inside the node ID, but each dimension has only 2 nodes in that case. Okay. That's this like it's not a ring, it's created by circles with only 2 points, multiple of them, and in n-dimensional torus being formed out of it. Tapestry turns out to be k-dimensional torus because there will be k digits. So there are n bits, so n by m will become k digits. So 2 raised power m array digits will be used. So 2 raised power m possible points will be there in each dimension in that case. We can now look at another alternative approach. I am not considering wraparound here, but it can be done. The algorithm is going to work without any problem. So let's look at what we do is each node is now supposed to maintain the closest node in each dimension. So in x dimension, it will now find out the closest node, which is going to be closest in Euclidean distance. Okay, I will not be considering anything with the same x value, but it has to be greater than x or less than x, but closest Euclidean distance. So everybody will do it, and it has to be done in all dimensions. Okay, so we will find out nx, which is going to be nx1, for example, or nx, if the nx is the value of current node, so nx prime, nx1 prime has to be found such that it is greater than or equal to nx plus 1, and the overall entry is such that the Euclidean distance with that node is closest. Okay, and if there are more than one possibility, choose the one with the closest value of nx. If nx is also same, then choose the closest value of ny, and so on. Okay, so that precedence has to be also specified. The same thing actually here also has been shown, that all these nodes are at same distance from the central node. So one up and one down I have to choose. So no entry should repeat in the routing table. So left side and right side, so value x greater than the current value, x less than value, and then y higher. So this 4 can be the set, and this is very similar to the way we use leaf sets in Pastry. But now, or in Chord we use predecessor and successor. So, but there are only 2. Here also we are using 2, but in each dimension there are 2 now. In Chord there is only 1 dimension, so there were only 2, predecessor and successor. Here there are n dimension, there will be 2 n nodes which will be there in this table. So this is basically n dimensional leaf set table. And now who will be the root node? Let's find out. So root node will be always the node with whom the Euclidean distance is minimum. So this value which has been shown, hx minus nx square plus hy minus ny square and so on, should be minimum. For a 2-dimensional thing, this other terms will not be present. So we find the node such that this happens, and that node will be the root node. If there are more than one candidate, then you will choose the higher of the values of nx. If nx values are same, higher of the value of ny, and so on. So this precedence rule also need to be specified and consistently followed for uniqueness of root node. So let's now take an example, the same example, but now we have to find out hash of 3,3, how this will be done in this case. Okay, now this case is not same as like this, where we were actually using, first of all, precedence of nx was taken, find out the closest nx, and then that is freeze, then find out the closest y. This is the way root node was found here. Here it is based on Euclidean distance. Okay, so suppose the same query 3,3 is available with 8,6, what is going to happen? So for an entry for which nx is less than 8, so we can choose, and it has to be closest one. So we can choose 6,4, which is the closest Euclidean distance. Then nx greater than that, there is no entry because there is no fold over, so there is no entry which is going to be having a nx greater value. Ny less, if I choose 3,5 will be the next closest entry because 6,4 has already been occupied. Ny greater, there is no entry. Now if we compute the distance of 3,3 from each one of these 3 options, 3,3 is the least one. 3,5 is going to have the least distance from 3,3, which is 4. So we just send over the query to 3.4. Now come to 3.5. So what happens to 3.5? How the routing table entry will be there? So for less than x, you find out the closest value, it will be 2.4, which is kept here. Okay. And then if nx is greater than that, then this 6.4 will be the closest entry because this is far off. Then ny greater than 8.6 because that's the only now possible entry which is available, which is closest. Ny less than, it will be 3.2 actually, because this is far off. If you compute the distance, all these are occupied. This one is also far off. This is the closest we will put there. So now when 3.3 is going to be measured with all these 4 nodes, 3.2 will be the closest one and the entry will be handed over to it. Now 3.3 and 3.2 essentially, 3.2 has to now build up its own routing table, which it will do. Higher side, the closest node is this. Lowest side, the closest node is this. Upper side, this is the closest node. Lower side, this is the closest node. Okay, so this will be the entry, and it will find out how far is 3.3 from each of these 4 entries in itself. So it will find this, it itself actually is the closest one. So it should be the root node. Same we can look for another example where hash ID of 4.1 is chosen and query starts 2.0. The same thing which I am repeating, but now with a different metric. So routing table at 2.0, what is going to happen? Nx is greater than, if I am choosing, then 3.2 will be the closest node. Nx less than, then 1.2 will be the closest node. Ny greater than, the 2 already options which were there are already occupied, so next best option is 6.2. Ny less than, there is no option. The query will be straightforward, will be handed over to 3.2, which is of course is the closest. Now 3.2 entry which is already available here, this is going to compare with all these 4 and you will find that 4.1 is closest to itself. So 3.2 is the root node in this case. Now this was not the case in the earlier thing, there was no Euclidean distance in that case. Okay. So if you go back and check, the root node which we found was for this 6.2 was the root node, while now we are actually having 3.2 as the root node. Okay. And for this one, root node was 3.5. Okay, it was not 3.2. Now in our case, if with Euclidean distance, both are 3.2 because that's if you look at that's actually closest. Now 3.2 will find itself to the closest and determines itself to the root node. But how these tables are going to be learned, the neighborhood tables. So actually I should not call it neighborhood tables. Those are normally used in the connotation of with the proximity metric. So the new node will attach itself to any bootstrap node and request for its routing table. And from the new knowledge which it gets, new nodes actually information, it will pick up the better options and replace the existing entries if it's better than the existing entries actually. So for example, new node is 4.3, it is bootstrap to 2.0. Okay, so 4.3 somewhere lies here. So 4.3 is bootstrap to this, so only 2.0 is known to it. So only entry is 2.0 as of now. 2.0 will now send its routing table to 4.3. 2.0 will not be affected by knowledge of 4.3 because it still is not the better option for already existing options. So 4.3 will now update its routing table because it now knows about this and this node. So 4.3 will now pick up, for larger NX it will pick up this particular node 6.2. For lower one it will pick up this one. For higher, because it's only know of these 3 plus this 4th node, nobody else is known, so there is no entry for ny greater. For ny less, it will again choose whatever the next best possible entry, which is 1, 2. So these 3 entries will be learned. In the next time step, it will come to know of new following more closer nodes actually. Okay, so for example 6.2 will be telling, so I am only writing the nodes which are closer. 6.3 will become aware of that, so 6.3 will get replaced, 6.2 will no more be there. It will learn about 3.2, from 3.2 about 2.4, so 2.4 will be learned. From 1.2 again about 2.4 only the knowledge will come, so that will also be replaced. This can be observed in the previous figure. So this guy will tell about this person and this person, but this is the new entry which is known is actually this guy. Okay, so 2.4 is what I have written. 2.4 will be learned from this. Similarly 6.2 is going to tell about this person, this and this. So it will learn about this new guy which can be its own possible replacement entry. This guy cannot be replacement entry, this nodes he is already aware of. So based on this, you will now replace these entries, and after this it will remain stable. And of course you can see for this guy left side this is the one entry, for right side this is the one entry, for up either this or this both can be there, so it can retain this one. Of course it will come to know of this one also. So if this is going to be with the proximity metric small closer one, so you can choose this one actually in that case. And this one is going to be now for the lower y, so 6-2 will again come. Okay, so this has gone in the x plus greater than x and nx greater than nx lower than ny greater than and ny lower than, again this will come. So that's the entry which essentially now gets reflected here. 6-2 comes here now, and this becomes a stable routing table. Now this is how the new nodes get inserted. When they get removed, again those entries are punched from the tables and replenished by the better entries when the routing table exchanges are happening. So through this example which was in 2 dimensions, one thing which is obvious that it can be extended to n dimensions, and each node need to maintain a leaf set of 2n node entries at max. Okay, there can be sometimes less also, but 2n node entries are required most of the time. And at every step hash ID is transferred to a closer entry in terms of the Euclidean distance. So each node has to maintain greater than and less than entries for 2 closest nodes in the table in each dimension, again closest by Euclidean distance. And as far as possible all 2n entries should be filled. So if you don't get best entry, you can find out the second best entry and fill with that. And of course with cyclic wraparound also this can be done. You can do precedence of one dimension over other, either doing distance that way or using Euclidean distance also it can be done on a n-dimensional torus. Then of course whenever more than one option is there, use proximity metric to further optimize the performance. Though in Euclidean distance normally all the nodes which are with the same Euclidean distance only will be the options available to you. So options will be less. So optimization also will be less compared to when you are actually choosing say tapestry kind of a structure where the options are pretty large. So this is how the distributed hash tables in multiple dimensions actually work, and this is the most generalized framework which can actually exist. So almost everything can be explained in this form. So with that we close the lecture now, and in the next lecture we will be talking about multi-layer DHT, where the multiple services will end up in using their own separate layers, and a node can participate in multiple DHT layers simultaneously, and of course while retaining the same node, which also means there will be multiple routing tables. That we will do in the next lecture.